Okay, so day 11. Let's try and squeeze this in so we're up to date again, because I left this hanging for ages. 11. Plutonian pebbles. Right. Alright, day 11. The plutonium pebbles. The ancient civilization on Pluto. And this was in... Oh my god, this one. This one was hard, wasn't it? I think this one was a bit tricky. No, was it? Actually, this might have been the easier one. There was one that looked similar, which was like on an infinite grid. This one doesn't look like it was an infinite. Oh, it had recursion involved. Regardless, I don't think this was actually that bad. This one was sort of like... Just have to think of the recursion as just going up a floor or down a floor. Alright, so... The ancient civilization on Pluto was known for its ability to manipulate space-time, and while the historians explore their infinite corridors, you've noticed a strange set of physics-defying stones. At first glance, they seem like normal stones. They're arranged in a perfectly straight line, and each stone has a number engraved on it. The strange part is that every time you blink, the stones change. Sometimes the number engraved on a stone changes. Other times, a stone might split in two, causing all other stones to shift over a bit to make room in their perfectly straight line. As you observe them for a while, you find that the stones have a consistent behavior. Every time you blink, the stones each simultaneously change according to the first applicable rule in this list. If the stone is engraved with the number 0, it is replaced by 1. If the stone is engraved with an even number of digits, it is replaced by 2 stones. If none of the other rules apply, the stone is replaced by a new stone. The old stone's number multiplied by 2024 is engraved on the new stone. Okay. Easy enough to code. No matter how the stones change, their order is preserved and they stay on their perfectly straight line. How will the stones evolve if you keep blinking at them? You take a note of the number engraved on each stone in the line. So you blink once, so that one becomes 1. The second stone is multiplied 2024. Third stone is split. That one is split. That one is multiplied by 2024. Okay. So the only real complexity issue is with the splitting. This is where you'd really would want a linked list rather than a Python list, but we can try with a Python list and see if it's okay. After blinking 6 times, you're... How many stones will you have after blinking 25 times? Hello, Maro. Yes, I'm finally doing 11. 25 seems small enough that we can just simulate it, but I'm pretty sure they're gonna throw a big number at us for part 2. So... Deceptively simple input. Okay, let's Alright, we'll just code it the obvious way and then have to think about what we do for whatever comes in part 2. Okay. So just stones equals int x for x in f dot read line. Okay. Define blink. So if you blink, then we have to go through each of the stones. Okay, we'll just do this the Python list way. It's not efficient, but it's only 25 times, so might be okay. So we want to do I equals 0 while we could iterate backwards over flip the list around and iterate backwards, or just do it like this. Say while I is less than length of s. So let's go growing s. Stone equals I. Alright, we have to check each of the three conditions. If stone equals 0, then we want to replace it with 1. Elif length of the string of stone divided by 2, then we want to split it. So we want to say left equals int just say n equals length the string of the stone, left equals string of stone to n over 2. Right equals string of stone n over 2 onwards. Entered. So let's just say replace this stone with left let's say s dot ins. S is a list, so it's s dot insert. Which way around do you do this? Hang on. index object. Okay. So that operation is the inefficient one. Everything else is fine. And then we want to increase I by 1. Else Si equals 2024 times Si. And then in all cases we will add 1. So we add an additional 1 if we've inserted one of these. Yeah. So for in range 25, link S, print S. Is it gonna grow that much? Brink stones, print stones. Let's just have a look. Print dot readline dot split. Oops. Okay, it's quite big. So is that the right number of times? 25 times. How many stones will you have? Okay. Print length stones. One 99986. Alright, correct. How many stones would you have after blinking a total of 75 times? Alright, fine. So hang on, my chat just disconnected. The stream is still fine. I have to log in again. Alright, so 75 times is obviously going to be too much. Wait, I'm having to solve a captcha to log back into my chat. I'm looking for fire hydrants and motorcycles. Okay, there we go. They didn't even bother to give you an example here. Yeah, well, they did. I mean, that is an example. Alright, so hang on. Stupid chat window's not working properly. Okay, so just to get an idea of the slowness, let's just try doing it and see when it breaks down. It's probably going to be around 30 or so. For I in range. Print. I don't know. Print. I. Ink stones, alright. Let's try doing... Oh, I don't have the thing open. Alright. Just... let's see how far it gets. 25. Well, we're trying to do 75, aren't we? Yeah, okay, it slows down there. Alright, stop. Okay, fine. One of the things which definitely improved this, though, is to use a linked list instead of a list. Because we don't want to be using linear time every time we're inserting. Nevertheless, I think the number's still going to be huge. But... Wait, how big was 25? 25 was 199,000. Yeah, it's going to be... No, we don't want to be actually storing these numbers. Okay. So... Okay, let's have a think. So odd numbers multiplied by 2024. So does the actual value of the number matter? Can we quickly see ahead of time whether it's going to end up with a... how many digits it's going to end up with? Not quite. Don't think we can quite do that. But it would never get... So what's interesting is that each of these sort of creates a new set of stones. So it's like we're solving hang on, how do I put this in words? So it's like we're solving... It's like we're just blinking that, and then doing this one separately, and this one separately, and then appending them all together. So... this looks like something we can use recursion for, so we can say, given a number, we want recursion with memoization, basically. So we want to say, in the general case, we want to solve this. We'll say define get let's call it span a stone. So I'm saying, if give me a single stone and I want to blink this many times, tell me what the final span is going to be. And this might be a case for us to use the thing that I don't use often. Memoirs? I don't remember how to use this. Let me Google this. I don't think that's how you type it at all. Python memoirs decorator. Memoirs. It's memoized. Man, Google results are such trash nowadays. They're just trying to steer us to use their AI. I don't want to make my own in memoized class. I want to find the one in Python. Python memoized decorator. Func tools. Here we go. Func tools. Oh, it's at cache. Okay. So do this. Cache. And from func tools. Alright, so usually I would, in the past, just create my own hash table and store things and check things and pull them out of the table. This just kind of does it all for you. So, and I believe it can be even more efficient than writing your own. Probably because it does some optimizations and stuff. So let's test it out. So we want so basically we want if similar to this, we'll say if stone is 0, it's going to be return get span. Oh, hang on. If number of blinks is 0. If num blinks is 0, return 1. Okay, so that's one. We're not blinking at all. We stay with 1 stone. Okay, that's the base case. If the stone is 0, we want to return the get span of 1. Num blinks -1. So otherwise, if the stone has an even length of number of digits, let me do that. Left is that, right is that, and then we should break it up, make 2 separate calls. Don't do this. We want to return get span of left numberlinks -1 times, and whatever that final span is, we concatenate it with the right. Right, numberlinks -1. Else, it's going to be get span of stone 2024 times stone numberlinks -1. So in theory, well, one important thing is this is getting rid of the list that's growing and growing. So we're always just finding the result for one single number. So if our cache builds up enough knowledge of lots of stones and they're not going to get too big, then it should just be like a summation of of that. So in theory, the result should be we don't do this anymore. Or, okay, part 1. Let's check if this gives us the same results. So we want to do print. So it's basically going to be the sum of, okay, num equals 25. Sum of get span x num for x in stones. Just sum the separate spans. Times. All right, let's test it out. $1,999.86. Okay, is that right? Sound, yeah. Yes, okay. 75 then. How fast do we think this will be? Is it 75? Yeah, 75. Okay. Instant. Correct. So that tells me basically the numbers never actually really get that big, or at least they don't get big often, because every time it grows, it's like there's a 50-50 chance of the string having like even length. So the chance of it getting really big diminishes with each growing. So basically there are very few numbers that get so big, and in general you're gonna get the split. Okay, so in general the numbers don't get big, and if they don't get big, that means we're basically covering most numbers in our cache. So if they appear again, you don't have to recurse. So all in all, pretty quick. That was just instant. So yeah. So like in the old days, I would have done this. I would have said, oh, hang on. Would have said table equals that, and then every time we have a stone and numlinks, we check like if stone numlinks in table, just give the stored result, turn blah blah blah. Like that. Otherwise, we compute the result, and then at the very end, we put it into the table before we return it. I mean, I could actually just finish coding this right now. Return. I'll take this out. Let's just see how it compares in speed. So we see result equals that. Result equals that. Result equals that. Well, here we just return. So result equals that, and then table. I can't remember when they introduced cache. It was probably quite a long time ago. I tend to not pick up on these things for a long time. Result and then return results, so it should do the same thing. Return Table. Yeah, and it's the same speed. But it's better to use cache probably, because I think it's doing some more. I think it's using like an LRU cache, so things which come up more frequently are kind of prioritized in the cache, so they'll get pulled out quicker. Whereas if you just use your table, then that isn't really happening. It's just searching the table uniformly every time, which is still quick because it's a hash table. But using the LRU cache, I guess, is more efficient because then more frequent things are getting accessed quicker. I use a table as cache and it was fast enough to, yeah, it's the same thing. So, but yeah, cache is cool. And that's how you have to solve this problem, surely. I don't think you can do it without some sort of caching. Well, when I say some sort of caching, you can do it without caching if you're going to compute things in a forward direction. So I could start from the do an iterative which doesn't use recursion, do 1s and 2s and work my way up. That would be the iterative solution, and it would avoid using stack memory, which is an advantage. But that would also work, I guess. All right, G12345. See you next time. I'll post my GIST code and my video later on. It was a nice problem, but it was, once you realize it's dynamic programming, it's usually easy to phrase it as a recursive thingy. Okay, there we go then. Alright, that was much quicker than I thought it would be. I thought, well, okay, that means I managed to squeeze it in today. I was worried I wouldn't have time to fit both in. Alright, I don't know if anyone else is doing Advent of Code. Actually, I don't really feel like grading right now. I just want to stop the stream. Alright, thanks for watching. And see you tomorrow for day 14. Bye-bye. Also, we're over halfway till Christmas. Things are going to get hard now.